Now, while the Friedel-Crafts acylation is an incredibly useful reaction, the major setback with that reaction is that generally we're not searching for a ketone, we're searching for an alkane. We want to get rid of that ketone when we finish. That's what you're shooting for. So let's say you want to get rid of that ketone and you want to form the alkane. So you want to completely cut that oxygen off. Well, there's three ways we can do this, and the three ways depend really on the functional groups associated with that benzene ring. So let's say we had this methylbenzyl ketone sitting up here on the top left, and we want to reduce it. Well, the fastest, most efficient way is to use HCl in the presence of a zinc mercury amalgam. And what this is going to do is it's a very brute force approach that will very quickly and very efficiently remove that ketone to give you ethylbenzene. Now, this is under highly acidic conditions, and this is the problem, that if you are working with functional groups that are particularly sensitive to acids, it may actually degrade your product. So an example I've got down here is this ether. So ethers undergo acid catalyzed Williamson ether synthesis. They can go back and forth. So if you throw this HCl in here, you may end up creating an alkyl benzene. You might end up breaking the ether apart. So a second option here is what's called the Wolf-Kishner Reduction. Yes, I had to write down all the little details because there's a lot that goes on with Wolf-Kishner. With Wolf-Kishner, you have a solvent, H.2NNH. You've got potassium hydroxide and triethyl glycol. I'm going to write this on the screen because I really don't want, that's going to be way too small for you to read. The big thing here is that this is a reduction under basic conditions. So something like an ether is going to be very stable when we're working with basic conditions, because to do the Williamson ether synthesis or to do acid catalyzed ether synthesis, again the name implies it, you need acid. So under basic conditions it's stable. The trade-off here is that this is going to be a slower reduction because it is a more gentle reduction, but ultimately you're going to end up removing this ketone. Now, let's say you have a compound that is sensitive both to acids and bases. In this case, I've written down here an acetic anhydride. Under basic conditions, we will form the carboxylate ions. Under acidic conditions, we will form the carboxylic acids. The easiest way we can do this is what's called the Mozingo synthesis. And again, I'm going to write it down here, but definitely up in your screen what it's going to be. For the Mozingo synthesis, this is a dithiol solvent, H2 and what's called Rainey Nickel. And the Rainey Nickel here is just a very high surface area nickel catalyst. Now, this is a very gentle reduction, and the only thing it's going to do is pick off our ketone. What's the trade-off? Why not run it all the time? Well, it's very slow. It's very time involved. The reason it can't break down this acetic anhydride is because it's not that great of a reducing agent. So we will still get our acetic anhydride when we do this. But we're going to do it over a very slow, very prolonged period. So these are your three options after you've done your Friedel-Crafts alkyl acylations. You can brute force it, HCl zinc, through the Clemmensen reduction. Very aggressive, but if you have an acid or base, if you have an acid sensitive functional group, you'll need to switch to the Wolf-Kishner. Wolf-Kishner is under basic conditions. It's slower, but it's still faster than the Mozingo synthesis, which, while it will guarantee that pretty much the ketone is the only thing that reacts, the Mozingo is a much slower, much gentler reduction. So this is how we can close the loop on our Clemmensen acylation, or Friedel-Crafts acylation. If we want to attach an alkane group, particularly through a primary carbon, we do the Friedel-Crafts acylation, and then we turn it around and reduce off our ketone.